Hello everyone, welcome to David Griffiths Electrodynamics. This is going to be problem 4.26 from the book. And as always, if you're new to my channel, welcome. And any returning subscribers, welcome back, guys. As always, just if this video or any of my other videos have helped you out along the way in your physics journey, feel free to leave a like on the video, subscribe to my channel. You know, it definitely helps me out and it helps to grow the channel. If you would like early access to my videos, you can check out my membership options as well. But besides that, let's go ahead and jump into the problem. So 4.26 is here on page 202. So we have a spherical conductor with a radius of A, and it carries a uniform charge Q. And we know it's going to live on the surface because it's a conductor, so all the charge is going to try to spread out away from each other onto the surface. And it is surrounded by a linear dielectric material with a susceptibility of chi sub E that has a radius of B. And we need to find the energy of this configuration. Essentially, what is the electrostatic energy it takes to assemble this sort of the free charge, like assemble this sort of conducting sphere with the free charge Q on it, surrounded by this dielectric material. Now, in the previous section, we derived this equation, which is the work done to sort of assemble the free, essentially what this is telling us is it relies on the fact that there's free charge in the system. The whole derivation of this equation relies on the free charge in the system. And what this is essentially telling us is the work done to assemble that free charge onto the system. So this is going to be the work done to essentially put that free charge Q onto the conducting sphere that is surrounded by this dielectric material. So as we add more and more charge, we're inducing more and more polarization into this dielectric, and eventually we'll get the total charge Q built up onto that conducting cylinder, and this work tells us the work that it takes to do that, essentially, due to the electric field in the displacement field D. So what we're going to need is we're going to need the displacement field and the electric field for all of the different regions. And we have three regions. We have the region 1, which I denote here, which is inside of the conducting sphere with the radius of A. Then we have region 2, which is the region inside of the dielectric material itself. So it's the region between A and B. So you're inside of the dielectric sphere, but outside of the conducting sphere. And then region 3 is just everywhere else, completely outside of both spheres. Now, this setup is essentially the same, I believe, as an example problem. And you can derive this easily by Gauss's law as well. So the displacement field, obviously, inside of the conducting sphere is 0 because there's no dielectric material there. And it's a conductor, so the electric field inside of a conductor must be 0. So the electric field is also 0 for R less than A. Now, the displacement field in the region between A and B, just given by Gauss's law, and I believe this is from an example problem. I want to say this is example like 4.5. Let me just verify. From chapter 4, example 4.5. Yes. Okay, so 4.5, example 4.5 is this exact setup, and we derive the displacement field and the electric field. So that's basically where I pulled this from. So I just use that result, and if you're really curious and you want to derive those again by yourself, just use Gauss's law to derive those yourself. It's pretty simple. But the displacement field is going to be Q over 4 pi r squared in the r hat direction for r greater than A. And that holds for inside of the dielectric material as well as outside of the dielectric material. And then the electric field in the region between A and B is going to be q over 4 pi epsilon r squared. And then the electric field in the region outside of both spheres is just going to be q over 4 pi epsilon naught r squared. So these are the relations that we're going to use for deriving the work here. So what we have to do here is we have to integrate this this dot product of these two, but over all of space, right, over everything. And that means we have to integrate across all three regions. So that's why we needed D and E for all three regions. So D dot E for region 1 is 0, of course, because region 1 is inside of the conducting sphere. And then I calculate D dot E for region 2. And so that's just going to be q over 4 pi r squared times q over 4 pi epsilon naught r squared, which is q squared. Oops, sorry, did not mean to scroll all the way down. Hang on. Oh, Lord. Oh, we changed problems. Okay, there we go. Sorry. It like scrolled to the next page. So D dot E for region 2 is q squared over 16 pi squared epsilon r to the 4th. Then D dot E for region 3 is q squared over 16 pi squared epsilon naught r to the 4th power. So I just go ahead and calculate D dot E for all three regions, because when we do this integral, since we have to integrate over all space, we have to split that integral into three integrals where the bounds range from, the different regions. So for region 1, we know this is going to be 0. This integral is going to be 0 because D dot E for region 1 is 0, but I went ahead and wrote that in anyways. And region 1, the R integral, of course, ranges from 0 to A. And I only write the R integral here because there's no theta dependence and no phi dependence in the displacement or electric fields. So the integral, the phi integral and the the theta integral will just be 4 pi for all of these integrals, because the integral of phi d phi is just from 0 to 2 pi is 2 pi, and the integral of sine of theta d theta from 0 to pi is 2, so you end up 2 times 2 pi, which is 4 pi. So I just leave those integrals out and just assume that we just do them intrinsically with these integrals, and we just tag in a 4 pi there at the end. So anyways, for the second region integral, it's going to go from A to B. R is ranging from A to B. And then, of course, for the third region integral, R ranges from B to infinity. And then we just plug in our actual values for these dot products here. So we have 0, of course, for this one. And then the second integral, we get this q squared over 4 pi, over 16 pi squared epsilon r to the 4th. And then this ranges from A to B. And, of course, d tau, this is a spherical volume, infinitesimal spherical volume element, which is written as r squared sine of theta dr d theta d phi. And so those r squareds are going to cancel 2 on the bottom. And then the third integral over here, we get a similar thing happen where we get the r squareds canceling on the bottom. And that integrand runs from b to infinity. Then what we end up here is we get, we end up having the integral of 1 over r squared dr, which is just 1. It's going to be minus 1 over r. And then we have to evaluate those at the bounds b to a and infinity to b. So this integral here ends up being minus, because of the integral, q squared over 4 pi epsilon r. And 16 pi squared goes away because the 4 pi from the phi and theta integral I tagged in, and that just cancels on the bottom, so we end up 4 pi on the bottom. And same for this integral, the 4 pi from the phi and theta integral cancel the 16 pi squared on the bottom. So we get minus q squared over 4 pi epsilon naught r. And then we just have to plug in the bounds for these two. So when we plug in the bounds, we get a nice little algebraic expression here. So I pull out the minus sign out front. Wait, no, I don't. This is an equal sign. But we have I pull out the q squared, and then I pull out 8 pi, because we still have that 1/2 out front from the relation for the work, and that's going to multiply the 4 on the bottom. So I pull out the 8 pi, and I leave the 1 over epsilon naught, and then 1 over r evaluated from b to a or a to b is 1 over b minus 1 over a. And then the last integral, of course, we get minus 1 over epsilon naught and 1 over infinity minus 1 over b, where 1 over infinity goes to 0. So we just get a minus, that's going to make it a plus sign there. We get a 1 over epsilon naught, 1 over b there for the second term, and the first term stays the same, except that I used the minus sign and I moved it inside of the parentheses to flip those bounds around. And then noting that epsilon is equal to epsilon r times epsilon naught, where epsilon r is 1 plus chi e times epsilon naught. So, or sorry, the epsilon r is just 1 plus chi e. Then we can rewrite this 1 over epsilon in terms of the susceptibility. So 1 over epsilon is 1 over 1 plus chi e times epsilon naught. So then we can rewrite the work as this, where I replaced 1 over epsilon with that. And then I can factor out a factor of epsilon naught, and we're just left with this, which honestly, like, this is fine. Like, I think Griffiths has it written a slightly different way, but I mean, there's no point on, you get nothing really gained from rewriting it in the way Griffiths writes it necessarily, so I just leave it like in this form. So this ends up being the total work done to assemble the free charge onto the conducting sphere, essentially, due to this configuration we have. This does not tell you the work, though, that's in the fields, I believe, as well as it doesn't tell you the work done that, like, the internal work done that, you know, that the molecules did to polarize and such. This is strictly, I believe, the work done, the work stored in the fields due to you putting all that free charge onto the sphere, I believe. So anyways, I hope this made sense to you guys. If this helped you out, you know, remember to leave like, comment, and subscribe. And as always, I will see you guys on the next video. See ya.